So Lorenz asked me to introduce Artur, so I was taken a bit by surprise, but since he's a good friend, so I mean, I'm delighted to do so. So it's a great pleasure to have Artur Avila this evening with us. So he's going to be in Zurich for about a month, so he's visiting the university currently. And so when I discussed with Lorenz that Artur might be visiting me, so we were very excited to have him here this evening at this Beiratssitzung. So Artur is so I'm not going to embarrass him too much by telling too much good things about him, but I have to, yeah, so you can Google his name and you will find plenty of information about him, but he is really an exceptional mathematician, and so he's from Brazil and also French citizen, so he had his PhD in Brazil on dynamical systems at the age of 21, then he moved to Paris in CNRS, was a postdoc of Jean-Pierre Yocos, who is a Fields medalist in dynamical systems, and from there, Artur published papers, made breakthrough after breakthrough, and so, not going to describe all the prizes he won, but he got the Fields Medal, which is probably the most prestigious prize that a mathematician can get, at the age of 34, 35, in 2014. And he was a plenary speaker at ICF, so every honor you can imagine, Artur had it, and he was also, I think you had the Légion d'honneur, Chevalier de la Légion d'honneur, so it was decorated by the French president, and so it's really a great honor and pleasure to have him this evening with us, so I hope this is
Okay. So thanks, Ashkan, for the invitation to come generally to visit the university, and thanks for inviting me to come in for tonight. I want to give an impression of my subject of research. It's difficult to. It's pure math. What me and my friends we work on, and. Which means that sometimes it has some applications to some different fields, and not only math, but in physics, for instance, and so on. But it's not our main goal. So usually we're quite focused on the internal structure of our subject, and we get into problems that are to be appreciated. You need to have kind of thought about the mathematical side other than the source of the problems. But I try to give an impression of what are dynamical systems and how it came to be, and what is one aspect, if I have time, like it's in the title, but what's this aspect relate to renormalization and which kind of systems it is, because that's something that I was more focused on. So, there are a few pictures here. Like I try to mention a few of them, to see that they all have to do. So there is this one, for instance, which is very well-known. So those are fractals, but why it appears naturally and how it relates to the subject. So I'm going to try to make you understand a few of those pictures. So, for instance, how does it start? So, dynamical systems can mean is a very extended subject that if you ask different people, they give different answer. I give one possible answer, which comes with a more historical motivation. Later on, it evolved somehow. But initially, it should start with Newton, with discovery of differential equations, and trying to solve differential equations. So so what did he do most famously? Initially, he get a gravitational law, for instance, so that let's not make things complicated and observe that it has changed since then. But already from the start, he had his law, and assuming that everything was correct according to that, he could tell you, as we learned, that with those equations, he can compute what's going to happen to a planet moving around the sun, if they are just those two things interacting. So then the solution, as we learn, is very simple. It goes through conic, so there is an ellipse movement of the bodies, and it doesn't, it looks pretty simple. You actually are interested probably in computing the equations, but what's more interesting is that kind of, it's always an ellipse. It doesn't evolve much, so after year and after year, if nothing else happened, no catastrophe or nothing exploded or no comet appeared and so on, it keeps doing the same. And so this is what happens, and it's very simple, and he computed everything for when you have those two bodies. And then there is the, initially you can look at more complicated systems, and one initial complication would be to have another body like Sun, Earth, and Jupiter. Like you would imagine that it has more influence. And then you can try to compute what's now the solution. It's maybe some more complicated curve that's going to be described by the bodies and so on. And in practice, you cannot actually compute, so there's no formula that you're going to get, but things are much worse. Once you realize that you don't get some nice formulas, you don't get them even in principle, and you realize that you should ask more basic questions. Like instead of saying what exactly will be the curve described by in long term by the planet, you ask even whether there's no catastrophe that's inherent to the systems. Like you could imagine that initially, as we know, it more or less describes an ellipse, but sometimes you say that because of the action of the other planet, things kind of move a little bit with time. So after 100 years, maybe there was some little movement of our ellipse, but still a little bit, and so on. Maybe there is this effect, and you might expect that this kind of effect would lead to some kind of perhaps periodic oscillation along very long time frames and so on. But it could be, in principle, much more complicated. Could you show that not something more dramatic happens, like after a long time, maybe things evolve so much that actually one of the bodies, like the Earth, goes very far away and kind of is not anymore interacting with the other bodies as strongly. So this is a possibility, so that arises, so that you have tried to understand the system instead of computing things exactly. Try to say something qualitative. Is there some stability in this system? And then, so this is a particular system. So here you have just a kind of basic things. You learned this in school. And one thing that you see this is the equations didn't change much. You can write down the Newton's equations, and then they are very simple. It's not the fact that the equations are simple that will mean that the problem becomes simple, because once you look at those simple equations, and it's just kind of, you can compute easily what happens at the moment. So that's what the differential equation says, how it's going to move from one moment to the other, but over a long time frame, then it becomes much more complicated. I have some example here of how, like I'm not going to describe in much detail, but let's see if this opens. Like this is another example. So that I wrote, so this is the graph of some transformation from the interval. So now instead of having some high dimensional space, that was the phase space for the previous case, now we'll just have something acting on an interval. So, our space is like the interval 0, 1, and it evolves from it's not anymore continuous time, but in discrete time from 1 year to the next year or whatever. It evolves according to this law. So you write some equation here. There will be the only equation in this description. It's just a formula like this. So it is just a quadratic formula. So there was a parabola. And it would be difficult to find, except if you had some kind of linear equation, that then it would be kind of very easy to analyze. It's difficult to imagine a simpler thing. So you could say, as I start talking about dynamical systems, let's say everything that we can about this should not be too difficult. So we have this rule. So, but the point of this, when working with this, is not kind of just to look this and describe as a parabola as kind of a static object, but something that keeps acting. It doesn't matter what happens from 1 year to the next, but then there's the next year and so on, and you look after a long time. So you do something that's, so iteration, it basically looks like this. So that's how you represent. I just took that map, and I took like 1 point somewhere, and probably got, this guy that's in this map. So of course you look at the position in the graph, and then you doing some procedure here, you're going to get the next position. So the points oscillate according to this, and it prescribes some trajectory and so on. And what do you expect from this kind of things? Then you see that you had some kind of, in the case of Newton, you had this kind of essentially periodic, quasi-periodic, in fact, trajectories that you have that essentially don't change. You are naturally kind of drawn often to try to look for some regularity in the process when you kind of let it evolve with time. So maybe there is, in the end, some kind of periodic movement here, where after a long time, the system will settle into some kind of orbit that, like, maybe it reaches an equilibrium, which would be a point that doesn't evolve anymore. For instance, if I started exactly at this point, right, it should go to itself, right? It's mapped to itself, so then it doesn't evolve anymore. So you could expect that maybe it settles down to something like this, or it settles down to something that oscillates between two movements. So you'd say that even years you have some behavior, and the odd years there will be some other behavior. And you might be interested in looking from this, starting with such a simple formula. If you didn't look at them, you might expect that something simple might be coming. And then you get this expression as you look. There was I don't know exactly what's going to happen for that parameter that I wrote. That was 3.8x times 1 minus x. In fact, you get a map of the interval for when 3.8 is replaced by any number between 0 and 4. So let us look in general what happens for those numbers. And then this is the graph that describes this. There is a range of parameters here that he has restricted from 2.4 to 4. So this is the parameter in front. So this gives more or less the height of that parabola. So it's always a parabola, but it can go kind of close to the top or not. And what's being drawn here is where the orbits kind of settle down, if at all. Like if you look at parameters that are kind of not, the parabola is kind of a little bit short. That point that I drew, that I pointed out, that would be an equilibrium, it's stable. And in fact, if you started from somewhere else, it should tend to settle there. It acts as we call a sink. It gets the nearby condition. So it starts there. It never kind of gets exactly there, but gets closer and closer. And at some point, basically, things are not changing from year to year. And then you see that once the parameter is evolving, eventually this equilibrium that you had, it becomes unstable, but then appears, there's a phenomenon of bifurcation that appears a period 2 orbit. So after you pass through this point, from this parameter, there will be still some fixed point, that will be that one, but it's no longer a sink. But it appears from it a pair of periodic orbit of period 2, which is represented here. So here is the phase space, so that's 0, 1. And here's the position, there'll be 2 points, and they'll be basically exchanged by the dynamics. And the orbits that you started essentially anywhere, they tend to kind of settle at this kind of period, orbit of period 2. So things are pretty simple still. And what happens, then you let the parameter evolve more, and it's still kind of, it keeps this stable behavior. And eventually you see this thing happening again. There will be a bifurcation, and then you get a period 4 orbit. And just after there is a period 8 orbit, and then things happen quicker and quicker, and eventually there will be period 16 and so on, and things will settle to something that will be like period infinity pretty shortly after. And later on, something complicated is happening here. So here, there is some kind of gray area where things won't be able to be described anymore by saying that things are settling down on a periodic trajectory. So that is basically the way you're going to describe this will no longer be through the system of things alternate from year to year according to some regular pattern, but you're going to need to look for different explanation of what's happening. And this happens if you took essentially the simplest formula that you could write down for an equation of the lowest number of variables that you could take. So you have one variable, you have a map of the interval, there's no topology, there's nothing. There is just the simplest nonlinearity that you could add, and you get this complexity. So that's the challenge of being able to say something intelligent about dynamical systems, is that you have to kind of take care of things get complicated very fast. So let me give you a flavor of what, so the other picture that I showed, how does this come from? This one, maybe if I had to click twice so that it would be bigger, yeah. So how does this one come from? So this comes from a guy that's called Lorenz, who was a meteorologist, I think. And then he tried to look at the equations that they use to try to model the weather are very complicated usually, but he tried to simplify it a lot. So they have some differential equation that he simplified, and he looked at something that had just 3 variables, which would represent, I don't know exactly what the variables represent, but it was an extremely simplified model. Maybe one was temperature, another was whatever, and so on. But there were just 3 variables, and they said, suppose that they just interact with each other without no complicated mechanism behind. Look at this, and let's take the equations, and let's put some equations. It was not very complicated, some polynomial with very maybe quadratic or cubic or whatever, and it's a differential equation, so it's continuous time. And then, well, now that's this simple, at least it will be my toy model that I look at this, and then I look at the more realistic system. And basically, once he just had this system, it was already very complicated, and it took years so that people could kind of describe what happens to this model. So what is drawn here is that you are in 3 dimensions, so this is a representation of a 3-dimensional phase space. And basically, you start somewhere in your space, it will evolve now in continuous time, and the solution will tend to go through this kind of object. They kind of move around here. There are this is called is a butterfly, and with 2 wings, and things kind of move around here, around this eye here. But sometimes it comes through the other eye and moves around. And what you see as behavior in this system, which kind of this is called an attractor. It takes you don't need to start here. If you start here, it will move a little bit outside, but then settles down this picture. This attractor is something that is closely related to, but slightly simpler than this other guy, this region here. This gray region that's written there, that's drawn there, it's kind of has some features that are in common with the behavior that you get for this kind of Lorenz map, which is basically the following. You could try to look at this and take a trajectory. And let me mention here that everything is deterministic. Like, though the equations are different from case to case, as the Newton's equations, they were completely deterministic. There is a rule that says how the system will evolve from time to time. There's no random behavior. There's no stochastic input. There's nothing. In principle, there's no coin being flipped. There's a rule. Exact rule. The other rule was pretty obvious. There was a quadratic equation. There's no term that's kind of hidden there. There's no noise. There's nothing. And here, that's an equation that's completely explicit as well, and so on. And still, if you take, now you took your trajectory and let it evolve deterministically, and you look, for instance, at those wings, and you can look at the moments that it is at this side and the moments that it is at that side. So it happens at continuous time, but you basically kind of chop and let us kind of wait for a few, give some discrete times just to get a sequence of events, left, right, left, and so on. And you look at what kind of sequence you get, and you find out that, well, it depends on how you started. This system here, the trajectories can do different behavior, but if you take at random, you're saying, like, let's take a trajectory that just selected a point, because in fact you don't know where you start exactly, but let's select one point, and just look at the sequence that you get. In this kind of things, sequence of left and right eyes that you get, they appear to be being produced by some stochastic process. Like, it appears to be randomly given. Someone is flipping a coin after you observe. Of course, there's no coin being flipped. But once it's here, it has to do a few things and so on. But in the long range, it becomes so impossible to predict. And it actually means that if you start measuring things and try to estimate what's it possible to say, like if I know that I saw this block here of lefts and rights at some point, and then I look at maybe what's going to happen later, and then there'll be another block of lefts and rights and so on. And I try to see the association between these and see if I can predict something by just knowing this. You discover that they behave to some extent basically as independent events. So that there is some kind of randomness that appears naturally without being kind of appearing in the equations. It appears because of what's known as emergence of chaos. So it comes, so that's just an explanation for this. And this is exactly, this happens already at that system here. This one here, the gray area, the theorem says that when you're around here, there's all stability, so it's what's called regular behavior. When you get here, you get a large chance like in parameters. So if you select your parameter here, and then the parameter is selected, it's fixed, and it's near 4. If you get exactly 4, it's going to be, there will be some exact formulas that will appear, and then it behaves basically like a coin toss with some kind of change of variables. So if you look at the kind of sequence that you get, of where you are in the interval, you're going to get basically a coin toss. But what's very interesting in the deep theorem is that it's actually, there is some probabilistic stability here. There is a large chance that if you take a parameter close to 4, that it will appear with some kind of description that's closer to stochastic than to kind of this deterministic description. It's very complicated also because you could like to say, well, okay, so when it's close to 4, then things are chaotic. And it's not quite true, because there will be tiny gaps here that become more and more difficult to see. So here you have some kind of white gap. So when you are at this kind of level, you have, again, stability. Here there will be a periodic opt of period 3 that you attract the conditions, that will appear suddenly for no apparent reason if you just look at the picture. But there will be kind of deeper windows here corresponding to periodic opts of higher and of different periods. And they will be all over the place here, tiny windows that will be kind of, there's no place here that doesn't have a window somewhere. And coexistence of this kind of, at every scale there will be some windows. Still, they don't fill up the picture. If you look at the measure of the set that's occupied by the stability regions, they don't get the full parameter space. There will be some measure that's occupied by things. But the set that remains is fractal. It kind of has it contains no interval, but it has a positive measure. Is a certain set. So that's kind of the difficult here. And then those are the simplest simple models to study. If you kind of, if I would be pressed to tell something about, now let us look at first example and tell, so what happens for the three-body problem? So you have the original thing. It's quite different in the sense of you have some kind of conservative system. So it's kind of Hamiltonian dynamics. So it has different flavor, but still there is space theoretically for chaos. And essentially to this moment, there is no understanding of whether chaos really could appear in a system like the three-body problem. It's a possibility. You know that some things can be complicated. You know that sometimes things are kind of, you can prove some stability of the system. So that's a kind of a huge part of the theory, which is to say basically that if Earth was very small and Jupiter was also very small, and then there was some kind of range of parameters that this happened, then so Jupiter is not affecting things that much. It's not a big planet, it's a very small planet. If all this happened, then probably there will be no catastrophe. But it gets like very probably that the Earth would kind of tend to kind of be more or less following an ellipse, and then you could wait, and then still would be more or less following the ellipse. But still it should be just, this is the best thing that you have, probably there will be. And, but we don't know at all if there is a tiny possibility that something very irregular would happen around Earth. Like you can prove in some situations, but what kind of irregular behavior is saying, like what I mean by emergence of chaos would be that the trajectory that's made by the Earth. Of course, in low time scales it would look like an ellipse, but in large time scales, if I start looking at very, very long time periods, I would see at some scale a sequence of kind of moving around that would be better explained as coin tosses or than some kind of regular behavior. So, so you have all those kind of limitations, and you could say, so the conclusions that you studied dynamical systems, you cannot tell anything about your systems. You just say it's too complicated to see. But there are questions that you can answer, not about very complicated systems, but for instance, about this one. One problem that was posed is, like I said, that you can predict things very precisely anymore. The question of whether what will be the behavior at an even year ceases to make sense, because it's not going to be a period 2 orbit. There will be no kind of seasonal behavior. And so you can say it makes no sense to ask where will I be in a very long time, at this moment in time, in a very long time. But there are questions that you can ask, and then since with this public, we know that you don't kind of need to abandon hope once there is randomness involved. So you ask precisely the question of whether there is some regularity there is in this kind of chaotic rule that would say the search for stationarity, for instance. So there is no kind of prediction exactly of where you're going to be, but there is a law. Maybe, could you get a probabilistic law that you describe, which would be stationary, that would say in very long time frames, I'll be basically distributed. I don't know where I'll be, but I'll be maybe here, maybe there, with probability whatever I'll be here, with probability whatever I'll be there. And this law would not change with time. If I wait for 1 million years is whatever, in 2 million years the same, 3 million years, but just after a long time frame, it will kind of settle down into some law. And even at this level, in general, it's not always the case. There are guys there that don't settle on a law. In a time scale of maybe 1 million, the behavior looks like something. In a time scale of 1 trillion, like numbers are kind of being made up, but at a different time scale, it looks like it's doing something different. And then in another time scale, it will look again different and doesn't settle into some kind of fixed behavior. So that's possible for here. That's the lack of stationarity. So there was some terminology of saying that the behavior is historical, that it evolves with time. But then there are theorems, so saying that we actually prove things. A big theorem that was proved in the 90s was exactly giving a satisfactory picture here that said that if you look at 100% of the parameters, there are exceptions, but they are tiny. And then with respect to measure, if you look at essentially anything that you pick at random a parameter and look what's going to happen, it will be, there will be a stationary law. Right? It will be described by something that is of two kinds. Either you have exactly kind of periodic behavior, so you settle in a periodic trajectory and then you are happy and the description is what you'd hope for, or you settle precisely into something that is very random. So that you settle into something that things will be distributed over an interval or a few intervals of possibility. So the probability distribution that your trajectory will try to follow will be something that's an absolute continuous measure. It should be described there, so it's not going to be focused on kind of very specific regions, but there will be absolute continuous distribution. And another property that it has, for instance, if you look at, I mentioned correlations that you can compute about the situation that you know now and what you know in a long time, and this thing that says that it behaves pretty much with very low correlation means that as time increases, the correlations decay exponentially. So that there is a very fast. So this is connected to kind of behavior of exponential instability as well of trajectory. So this kind of comes a little bit earlier, but there is what's called the post-Lyapunov exponent, which means basically that any imprecision that you have on the position of your trajectory, it's magnified very fast. So that's a deep theorem, which is about a simple thing that whose proof involves a lot of interesting mathematics that connects many other things, so that there are contributions from many branches of math to get to this theorem. One example, so this theorem that I mentioned is by my co-author Misha Lyubich, which gets us that the techniques involved here takes us to this kind of things also. Like a lot, not, it's just, what's this? So that's our counterpart to that picture that I had. There will be one that will make it more, just took this one because it's pretty. It's the counterpart for our parabola and for the parameter space of that. So that's a picture in parameter space. So instead of taking quadratic equation and iterate on the interval, we do it in the complex plane. So now the variable x, which was in 0, 1, was just replaced by a variable z that is is just in complex plane C. And what's represented here, this parameter space, the complicated picture is a zoom of parameter space of what is interesting. Like there is this kind of blue region that's outside, and this is a piece of what's called Mandelbrot Set. And the thing that's decorate, the black part is certainly in the Mandelbrot set, but there are many other tiny components that are difficult to see that accumulates in this kind of spirals and so on. And what's represented here is the following. You look at a very simple property of the system. So you have a variable z, and you have a parameter space c. So for each c, you get a dynamical system that takes z, maps to z squared plus c. It's one of the simplest formulas that you could write. That's kind of interesting. So it takes z, goes to z squared plus c, and you ask the following question. Start with 0, for instance. That kind of is special because the only place that has derivative 0. So it's called critical point for this map. So you start with 0. It's kind of more special, and iterate. So first time it will be c, then it will be c squared plus c, and then c squared plus c squared plus c, and so on. And ask the question, does this remains bounded in the complex plane, or does it grow more and more? Once it got a little bit big, let's say that c equals 1, and it was like, and at some point it had size 10. Then next time it will be like 100, and then maybe you subtract 1, but then it's still much bigger, and then once you take the square, it will be much bigger, and so on. So once it gets a little bit big, it kind of grows forever. So, it might go to infinity, or it might remain bounded. It cannot oscillate. But maybe not. If c equals 0, then it should be 0, 0, 0. It never changes. So there can be a fixed point. And then there are a few situations that are here. So what's the Mandelbrot set? Is the set of condition c, of parameter c, for which you don't go to infinity. And then it's generally drawn in black. Here is drawn in black. So here, this thing here is a set of parameters with this property somewhere. What's blue? It's just that it gets a little bit difficult to see the details here. So in order to see, you have to approach the set. All here, there are little points that belong to the set. And the color says more or less how distant you are from the set, measured according to some rule. So blue regions are a little bit further away. The warmer color, yellow here is a little bit closer, but then it switches against the blue for some reason because it had finite many colors. And what's interesting, so there are theorems about this set. Like what people try to prove about this, as an example, is that so one theorem says that there are this kind of tiny regions here. There are black points here. There's a way to go from this black point to this other one here. So it's actually a connected set. So that's one theorem. I'm going to show the full Mandelbrot set soon, but you can come. And one question that one of the main, if you want to know what gets people in this field awake at night, a deep problem that's one of the main things in here is to show that you can come between pieces of this. So from here to here, you can go, there's a way to go here. Probably you have to come here and then come here. It's connected. To show that you don't need to go far away, so what's called a local connectivity. You can, if you have 2 points that are close, they can be connected through a piece that's kind of doesn't need to be overly large. It looks a little bit too specific question. Why do I care that? But actually, I can't explain. It's connected to deep problems, called rigidity problems and things so on. So the question is not related just because I want to understand how the set looks exactly, but it tells us a lot about some specific features of rigidity of certain dynamical systems that you cannot kind of change them in certain ways. Just so that it makes clear the similarity, there is this picture that shows that the 2 pictures are connected. So there is the features of this. It's just the real slice. So if you set the parameter c equals to be real, you'd get this part. You get the whole interval, but you can see the shadows of this in the complex plane, so corresponding precisely to the bifurcation diagram. So that's an interesting. An interesting thing, and I mentioned an open question, so that's the full set. This is what I said that's connected. Understanding of what's the nature of this big, so there are kind of big dark regions that are kind of that are interior regions of the set, and then there is the boundary of the set where with filaments and things like this, and trying to understand what are the bubbles and how can they appear and which kind of dynamics in these bubbles is another deep problem here. Another thing that can be seen here is exactly that takes us to the last part to the last part of the title. That's the full Mandelbrot set. Okay, so that's just the part downstairs. And here's the other picture that appeared. It was just a zoom somewhere, I don't know where, of the Mandelbrot set, like here. And it looks just like the previous one a little bit turned. And why is there that it appeared a copy of the whole picture inside the parameter? There's no simple explanation. There are many fractals that are kind of very simple to understand, that they look the same in large scales, in small scales. You know probably, how to say that snowflake whatever, and then there are all those curves that you can do, and I forgot their names, Sierpin's gasket and things like this. And so there are all those kind of things that are known. And there's a very simple explanation, because you produce your whatever, your fractal set, by doing the same procedure at a smaller region. Here there's no such a simple explanation. And in fact, it looks the same, but it changes all the time. If you look, it's a much more complicated. You're not seeing always the same thing. Probably easiest way for, of course, you can just, if I go to the Mandelbrot Set, it changes all the time. So there are a bunch of people, there's no internet connection. There's a bunch of people that, there's a bunch of people that kind of explore here, and there'll be some part that will be called the elephant valley, because there will be parts of this that looks like, that appears that's one elephant following the other. There'll be some kind of thing called the seahorse, whatever. There'll be some things that look like a seahorse, and then people find this. And it always changes, because it doesn't come from this. It comes from a more complicated interaction. And then, so this picture here, it was discovered by, so interest started when computers appeared, because nobody suspected before the computer images appeared that there would be such an interesting features behind the simple equation. So the first pictures appeared, and people started asking questions, and people saw, for instance, this thing, and they created a theory that explains why there is a copies of the whole inside. And then this theory is called, is one instance of what's called renormalisation theory. So renormalisation theory is something that's applied for certain systems that are kind of intermediate complexity. So what happens that if you have very simple complex, like this regular behavior, of course you describe it very well, it's relatively simple, so that it's periodic behavior. And chaos, enough chaos is good. If things are so given by an invariant, absolute continuous invariant measure, and you have this stationary, then you know that things have like exponential decay of correlations, and you can actually compute things by doing this. So like things that are random enough, you can compute them. Something appeared here that's practical. There was actually some, like there are people that make YouTube videos about this also. Like these are Julia sets, and there'll be a gallery somewhere. Oh, this probably, where's the Elephant Valley? Somewhere. Seahorse Valley, for instance. An elephant, oh yeah, seahorse. So that's kind of appear somewhere, these kind of features, and they change all the time. So that was the point. Anyway, this renormalisation theory, what does it, what it means? You're trying to understand systems that have intermediate complexity. Those are kind of the nasty ones, because you cannot kind of just say, well, things will be like if I am kind of throwing, flipping coins, and then I just can predict things, not exact position, but I can predict average. I can predict what's the exact correlation between some things, and then I can say many interesting things. The other case is fully deterministic, but the intermediate case, you don't know. It's very difficult to say anything about this. So a lot of our work is to try to get rid of the guys that would be in between, or trying to understand them better. But they exist. You have to show that they are not kind of, you can almost ignore them, but you cannot ignore them if you don't understand them to some extent. So you make a long effort for that. And the renormalization is useful for that. So what happens is that in the system, you're looking at something that you look at a small region of space that you let evolve, and you let it evolve for a long time. And after this long time, what you get has some complexity. It didn't kind of become extremely complicated, but then didn't become very simple. And what you see is basically of the same order of complexity that you had in the original system. So after you waited like for time 1000, and look at a very tiny place, and look at what happened after you waited for this, you see I get again something which was as complicated as the original system. So I try to analyze it now at this scale as being a system of the original kind. So that explains why you could, if this happens, you could get a copy of everything in that time, in some tiny scale. And then you try to understand how it evolves. And what's interesting here is that it looks a little bit hopeless, and that it looks like you're doing a very big deal, because what you're doing here is that the formulas, so it's not done at level of formulas, because here you started with z squared plus c, you waited for time 1000, you iterate z squared plus c, you got still a polynomial, but now the degree will be enormous because it kind of raises all the time, so you kind of get a huge degree. So the formula will look very ugly, so that the formula gets more and more complicated. You look at features that say that it has some kind of nice behavior. For instance, if I was in the real case, which was that there was a parabola, like you would not care that you have a quadratic equation. You'd care that you look like a parabola. Like that is not doing like this, but just doing one flip here. And then, so this would call a unimodal map. So this is a quantitative situation. So you'd say something is renormalizable if I look at some piece of my space, I let it evolve, and I get, again, something that looks like a parabola, like just something with one turn. Okay, and how do I use this to understand? How do I use this to prove theorems like the one that said that there is full stationarity? Okay, I just explain the connection with that theorem. So surprisingly, what do? You take the space of everything that looks like a parabola, for instance. Or here, you look at the space of everything that looks like a polynomial. It's a little bit more complicated because complex holomorphic functions are more rigid than real functions. But okay, so let's think about the real case. So look at everything that looks like that is unimodal, and you try to see if you find this copy there. And then there is this procedure that says I change my scale of space. I look at tiny region, and I look at a different time, a long time frame, and this becomes my time 1. Time 1000 becomes time 1, and my tiny regional space becomes my full space. After this procedure, that's the renormalization procedure, I have something that associated to my original system, which was, could be a quadratic system, but could be any other, gave a new system that now is another polynomial, but the features is that it takes a unimodal map to a unimodal map. And there is this procedure, and now you kind of iterate this. So you have some kind of rule to associate a dynamical system to another dynamical system. So it's a function in the space of dynamical systems. So we started with something what's just simple in one dimension, and suddenly you have something that's infinite dimension. And you have a rule, so that's a function, but you don't look at it statically, because once you have this rule, you can kind of apply it again to look at tinier and tinier regions of space and kind of longer and longer time frames. So you have actually a dynamical system in the space of dynamical systems. So that is kind of a meta-dynamical system that's kind of lets things evolve at the functional space. But now we are making a bad trade. We are trying to understand one dimension, and you have infinite dimension. You have an operator that has a very complicated expression. And what can you kind of say about that? Miraculously, you can say things. So a lot of things were proved about this. And the most interesting things are related to that. This kind of system that you get after this, so it's the renormalization operator that's suitable to understanding things that don't get overly complicated and that they are not too simple. So kind of intermediate level of things. Because if things were chaotic, every time that you would look at tinier scale and long time frames, it gets more and more complicated. So you don't get the same thing, but you get some more complicated systems. So there's a right region, intermediate region, where it's kind of useful. So this system that's designed for kind of not too overly complicated, not chaotic system, as an operator in this space, in this infinite dimensional space, it is in fact a chaotic system. So it has some behavior that looks like this Lorenz. It's a version a little bit kind of easier to describe. In fact, once the formalism is made, is given by what's called a horseshoe. But basically, that if you look at some features of this, there will be this process that you get sequence that you can produce any kind of sequence appears. You get you don't get some kind of rules. Everything is possible there, and it's an example of a horseshoe is an example of one of those call it hyperbolic or systems that are kind of model chaos. And then now you traded everything for kind of a chaotic system, let us say, in infinite dimensions, and somehow from all this. Because as we told that chaos is kind of like one of the nicer cases that you can analyze, with all this, then they proved that theorem. So Leibniz did in that case. He proved that they said that there is almost always a stationary law, because the guys that are in this intermediate region that I just described are the ones that kind of have a bounded but not infinite amount of complexity at infinitely many scales that are called infinitely normalizable. Those guys, they have to be rare. So he proves that those corresponds to a zero measure set in the parameter space. Because essentially, whatever in parameter space, so what basically he showed was that in parameter space, and then I finish just to make sense of in parameter space, he showed that whenever you have a system that is infinitely normalizable, you are going to find, because of this procedure that of chaos that kind of amplifies whatever you are having to a larger scale, and it amplifies actually exponentially fast, you are going to be able to amplify what happens. And he shows that when there is this kind of gray region where there's very little white window, but he showed that if you have a part that has this kind of bounded complexity, then near it you're going to find nice big gaps here, so which correspond to deterministic behavior. So whenever you have bounded complexity, there is nearby deterministic behavior, and since there are holes everywhere, you get in the end this system. So like, if I don't have any more time, but just if there was another picture probably here that if you want to look and try to find out what it is about, it's another nice picture. And this also, there's a renormalization theory behind. So this is, they call it the Hofstadter butterfly. Hofstadter is the guy who wrote, well, he's a physicist, but he wrote GDOSK. Maybe some read this book. But before that, he was a physicist and gave the name to this and analyzed it a little bit. And there are fractal features here, and this is something that's not yet fully understood, but there are many theorems about, and it arises here as an example of a dynamic. This is because there's a dynamical system that's related to a problem in mathematical physics. So this is in quantum mechanics actually this appears, and this is related to this kind of picture is related to quantum Hall effect and things like this. So there are kind of nice mathematical physics around this, but the mathematics is even better. And if you now, after the talk, whoever looks there will understand what it is this about, what are the equations that are not very complicated for this about, and then some features about this picture, they are included on what people call the 10 Martini problem. That's a problem related to this, is exactly about this kind of things, and so on. But just to mention, fractals appear, like when understanding some specific quantum mechanical object, sometimes some dynamical systems appear, and the analysis of these dynamical systems reveals that there are kind of these self-similar regions, and sometimes there is a renormalization picture behind, and you use this, and in the end you prove actual theorems, and you understand better these things. It's not just kind of a nice virtual technique that's completely impossible to make work.
Okay. Thank you.